Thank you, Justin. Thanks for the invitation. And thank you for coming to my talk. So nice to be back at Macquarie. And I'm going to tell you a little bit about generating random graphs with useful properties. And I thought I should start at the beginning. So the first thing I want to do is convince you that graphs or networks are kind of useful, interesting, something we might want to study. So here is an example that we're a little bit too familiar with after the last few years. This is a graphic from a conversation article from December 2020, and you can see a contact network. So the nodes or vertices represent people, and there's an edge between two people if they have interacted recently, I presume. So I think, yeah, the general person in the street is a little bit more familiar with networks now than they might have been a while ago. Here's another example that I took from a ecology journal. It's one of those nice pictures that they say we're allowed to use in our talks, and it's a food web. So the vertices represent species. We can see some animals, and in the middle, the green nodes are plants. The dark green nodes are weeds, and the light green nodes are crops. And there's a line between two nodes if one of the species eats the other. So that's representing a very complex sort of ecosystem with a graph. A little bit closer to home for me, let's see, I did two. Let's go back one, is a collaboration network. So there's a mathematician called Paul Erdős. The backwards button is a little bit less responsive. There we go. Paul Erdős worked a lot on random graphs and in lots of other areas, and notoriously collaborated with a lot of people. So this is a collaboration graph for Erdős drawn by his colleague Ron Graham in the 70s. And if you've written a scientific paper, you probably have a finite Erdős number, which is your distance to Erdős in this graph. So here's Einstein, and he has an Erdős number of 2. So if you're a physicist, you probably have a path to Erdős through Einstein. I did do a little update to this picture at some point to add myself into it with an Erdős number also of 2. So my Einstein number is at most 4, and actually I think it is 4. So you can play this game yourself and figure out what your Erdős number is. If you've ever been in a film, you also might have a finite Bacon number. And if you've ever written a scientific paper and been in a film, you can add those numbers together and you'll get a finite Erdős Bacon number. Natalie Portman and Mimi Driver are both have finite Erdős Bacon numbers, so this does exist. Anyway, we've seen some very serious and important examples of graphs describing systems, and we've seen some silly ones as well. But I hope that this is some evidence that it's worthwhile looking at graphs. Graphs are kind of everywhere. Our world is highly networked. So graphs are useful for describing relationships between pairs of objects in some big discrete system. I guess I might click that little picture, message, go away. Okay. I'll give you a definition of a graph. So mathematically, when I'm thinking mathematically, I'll say graph, and when I'm thinking applications, I'll say network, but they really mean the same thing. So mathematically, a graph consists of a finite set of vertices and a set of edges, and each edge is an unordered pair of vertices, so a set of 2 vertices. With this definition, graphs are simple. So an edge joins 2 distinct vertices, so you don't get a loop. And it's an edge set, not an edge multi-set, so you don't get repeated edges. Other places you might see different definitions of graphs, but I think this is the most standard for graph theorists. And I also know the sort of names of all the vertices, so that I can tell the vertices apart. They're labeled. We may as well assume the vertices are labeled with the first n positive integers, which I'll denote with this square bracket n symbol here. Okay. We often don't draw the vertex labels on the picture, however. So here's a really pretty graph called the Sekeres snark, which was discovered by George Sekeres in 1973. He was a friend and co-author of Erdős, and he was also the first professor of pure maths at UNSW. So this has 50 vertices and 75 edges, and it has some nice properties, which I'm not going to go into. You can see it's very symmetric. It has 20 different automorphisms, so 20 distinct symmetries, which is quite a lot. And one thing I'll also mention is every vertex has exactly 3 edges coming out of it. So every vertex has 3 neighbors. And we will also say later that every vertex has degree 3. This is the last time you'll see such a pretty graph even referenced in this talk, because if you're working with a real world network, it's very unlikely to look like this. It typically would have no symmetries and would have wildly different degrees. And also if you take a random graph from some set of graphs, it's also unlikely to look like this. So some graph theorists get to play with these beautiful objects. That's not what I do. Instead, let's have a think about this situation. Let's say, and this might even be true for some of you, I don't know, but let's say you have some complex discrete system, a real world network that you're interested in, and you've noticed something that you think is interesting about this network. Now, maybe it has a lot of triangles or some other small feature. And you will ask yourself, if you're a curious type of person, let's see, yep. Is this feature actually significant? Does it mean anything that it's there? Is it somehow arising because of the function of this real world network, or is it somehow just there by chance? If you grabbed some similar graphs, would you expect to see this? So how can you answer a question like this? Well, it's sort of similar to something that we either still do or certainly used to ask our first years to do, which was to think about if you flip 15 coins, and you notice that 12 of them come up heads, should you be suspicious that someone has tampered with your coin? It's a biased coin. So a fair coin should come up heads with probability exactly a half. Is this enough evidence that the coin is not fair? What we want the students to do is to compare this experiment to what you would get if you did use a fair coin, right? With 15 flips and exactly a half probability of heads. So the number of heads now has a binomial distribution where we remember that in a binomial distribution, there are n trials, they're independent of each other, and the success probability is p, right? Independent is important. So the students should write down a tail probability. We didn't just want them to calculate 12 heads probability, but may as well throw in the whole upper tail, at least 12 heads. How likely is this? So you get something like this. I've actually written down not many tails rather than lots of heads, but it's the same thing. And you get a number which is less than 2%. So now whether you or not you think this is significant evidence, that's not a question I want to touch. So that's, it's context specific. But the point is that what the student is doing here is choosing a null model to compare their experiment against. The null model is the fair coin flipped 15 times. Right, so that's familiar. So now we go back to this researcher who has this feature. They want to know if it's significant. And what they need is a null model that they can compare their network against. And in this context, the null model is a random graph, okay? So that's one possible motivation for why you might want to study random graphs. But if you don't like that one, I have got more. So maybe you have a hypothesis about your real world network, but it's really expensive to test that hypothesis. I don't know, you have to go to the Large Hadron Collider or something, I don't know. So if you can model your situation with a graph, you can run simulations in a computer. If your hypothesis looks like it's correct, maybe you decide to go away and do the expensive experiment, okay? Or you might have an algorithm that you've written that runs on graphs as input, and you've figured out the worst case complexity of your algorithm, but you want an estimate for the average case complexity. Then you could generate a bunch of graphs and feed them into your algorithm and see what happens. You're looking actually less convinced by these ones. So here's my motivation is basically it's interesting, it's challenging, it's fun, okay? So we want to look at random graphs, but which random graph should you choose to look at? Well, again, we'll start at the very beginning. So what if you want to choose just any graph on n vertices on the vertex set 1 up to n, each equally likely, so uniformly at random? This is super easy to do by just flipping fair coins again. So for each possible edge, independently flip a fair coin. If it comes up heads, you put the edge into the graph, and if it comes up tails, you don't, and that's all. So you just flip these edges, coins in any order, and eventually you'll flip all of the coins and you keep the edges that come up heads and throw away the ones that are tails. Of course, you don't need to do this with coins. You can think about product spaces and just work with the probability, but I think it's a nice thought experiment. So I tend to think about it this way. Okay, and you can check that each graph is equally likely to come up. Now, To talk about the properties of this graph, we'll introduce the degree of a vertex formally. So it's just the number of edges containing that vertex, which is the number of neighbors the vertex has. Like in the Sekera-Schnack, they all had degree 3. Okay. This first random graph model, the uniform random graph, is very dense, both globally and locally. So the number of edges on average is about half of the full number, which is n choose 2, the number of ways to choose 2 distinct vertices. And the average degree of a vertex is a half of the maximum possible degree. So it's a half of n minus 1. And that's too high for most real world situations. So the first thing you could try to bring that edge density down is to replace your fair coin by a biased coin, which has probability p, but this time you want p to be smaller than half. So p could be a small constant, or it could even be a function of n that tends to 0, okay? And this is the binomial random graph GNP, which is very, very well studied. And of course, if you take p equals a half, you get the uniform situation back. It's called the binomial random graph because the number of edges follows a binomial distribution and the degree of each vertex also follows a binomial distribution. Moreover, click, yep. Unless your probability p is very small, tending to 0 very fast, the degrees will also be pretty well concentrated around their mean. So none of them will be too different from each other. And this is an example I took out of a, now I've forgotten the word of it, some sort of data science textbook. That's what I'm looking for. A data science textbook that talked about GNP, which I thought was nice. It was written by some theoretical computer scientists. If epsilon is positive and p is at least log n over n epsilon squared, then all the degrees lie in 1 minus epsilon times pn, 1 plus epsilon times pn. So this is just an example where the degrees don't vary much. And this has been observed for a long time, but real world networks also don't look like this usually. The degrees are not concentrated. In fact, they're often heavy-tailed distributions. And this is a kind of old, like early internet picture of this. I don't know, those colors make me think old picture. On the left, we have the binomial random graph, what sort of degrees you get out of this. So the y-axis is the number of vertices with that particular degree, and the degree increases from left to right. So you see a kind of discrete bell curve with a binomial random graph. But in a real world network, you see something like a power law or some other heavy-tailed distribution. Not all the time, but quite often this has been observed, which means lots of vertices have a very low degree, but you do get vertices with very high degree, higher actually than you would expect from the binomial distribution, although that's not so visible in this picture. The main point is these graphs look nothing like each other, the pictures, right? So the conclusion is that if you want to use a random graph to model some real world network, probably you don't want to use a binomial random graph because it's not giving you the right degrees. By the way, feel free to ask me if you have a question at any time, okay? Good. So what can we do? Well, one thing you could do is go all the way to full control and say, I want to specify the degree sequence of my graph. And you might say, whoa, hang on there. That seems like going a little bit too far. You might have missing data in your real world network. You might have people lying on their surveys about whatever it is. You might not know the degree sequence exactly. But I still say this is okay because you can first choose the degree sequence randomly in some way and then apply, then look at the set of graphs with that degree sequence. One way you can do this is just to generate all the degrees independently from some distribution and condition on their sum being even, which is what you need. Yeah, I was supposed to talk about the definition. So we want to talk about the degree sequence of the graph. And I'm just going to say the vertices are labeled 1 up to n. Just write the degrees of those vertices down in order, okay? We don't assume that we've sorted the degrees into non-increasing order or anything. We just take the degrees as they come. So here is a graph with the vertices labeled at 1 up to 6. Vertex 1 has degree 2, and so you see a 2 in the first place in that sequence and blah, blah, blah. Also, we say a sequence of positive integers is graphical if there is a graph with that degree sequence. And so I tend to say degree sequence when I probably should be saying graphical sequence. I tend to use them interchangeably, and we'll only be thinking about graphical sequences. Also, I said positive integers because we can just ignore the degree 0 vertices and add them in at the end if we really want to have some. Okay, so yeah, That's the definition of degree sequence. And now we're going to look at, this is what I was talking about before, we're going to look at the problem of generating graphs with a given degree sequence. We fix it at the start. This is where I go, oh, but that might be overfitting. And then I say this bit. You could apply this to a random degree sequence where you draw each entry independently from some distribution. And there's also an algorithm for efficiently generating graphs with a given expected degree sequence. It's a very fast algorithm by Chung and Liu. And there's more details on this kind of thing in a really nice book by Van der Hofstadt, which is available online, like you can download it. Okay. So I still, this is my justification for looking at graphs with a fixed degree sequence. Okay. So let's define the set of all graphs on the vertex set 1 up to n with a given degree sequence to be G of D. The D is boldface because it's a sequence. And if the sequence is regular, all the vertices have degree D, which is not boldface, then we're going to use 2 arguments, G and D. Okay, so 2 arguments means the graph is regular, all the vertices have the same degree. Really, we're doing asymptotics. We're letting n tend to infinity. And so for either every n or for some infinite subsequences of n, we have a degree sequence. The length of the degree sequence is n, but also the elements of the degree sequence might be functions of n. But this notation, G of D of n, is really clunky. So I just write G of D, but we think to ourselves, we have one of these for each n. Yeah, and I'll use standard asymptotic notation, but sort of say in words what it means. The problem with working with graphs with a given degree is you no longer have independence of edges. So if a vertex is full, you can't add any other edge into that vertex. And this just makes life harder to do calculations and harder to generate randomly. So it's harder than working with the binomial random graph. Okay. But there's a nice workaround if the maximum degree is not too large, and it's called the configuration model, attributed to Bolabash. It also arose kind of implicitly in the work of Bender and Canfield, and also Nick Warmold around the same time. So we start with n cells, which are the ovals, and the jth cell contains dj points, and all the cells are labeled and all the points are labeled, so we can tell them all apart. Capital M is the sum of the djs. And we just randomly pair up these points, which you can do exactly uniformly and efficiently, very easily. You just grab an unpaired point and uniformly choose its other endpoint from the unpaired points and keep going. So once you've chosen your uniformly random partition, you just shrink all the cells to vertices, and now you have a multigraph with the desired degree sequence. It may have loops and it may have multiple edges, which we don't want. So if it does, we just throw it out, choose another random configuration and try again. So it's a rejection sampling algorithm. And when you finally get a graph that's simple, you output that as the result of the algorithm. Okay. Now, the good thing is that every graph from G of D is simple and they all arise from the same number of configurations. You just have to wire the dj edges up in dj factorial ways into the jth cell for each j. And the upshot of this is that the output will be precisely uniformly distributed from G of D. The question is, how many trials are you expecting to take before you get a simple output? Okay. So the expected runtime is some constant times capital M, the sum of the degrees, divided by the probability of being simple, because the number of trials is a geometric random variable, and that's the expected number of trials you need. So people had to analyze the probability that a randomly chosen configuration is simple. And in particular, if the maximum degree is order square root log n, then the probability of being simple is bounded below by 1 over some polynomial in n. So it's no smaller than polynomially small, which means you're going to get expected polynomial runtime. Whoops. But the square root of log n is not growing very fast. So we're allowing the maximum degree to grow a little bit, but not very fast. Can we do better? Okay. So Nick Warmold and Brendan McKay had a good idea. They've had several good ideas. And one of their good ideas was, we are rejecting this configuration if it gives rise to just one loop or one repeated edge. Can't we do better than this? We're being a bit wasteful. So they thought, take a configuration, only throw it away if it's got too many loops or too many doubles or, I don't know, some big multiplicity you don't want to see. Otherwise, work on it bit by bit using something called switchings to turn it into a configuration that will give you a simple graph. And a switching is a small local change which is designed to fix up some defect, like maybe you take a loop and an edge and rewire it so you get rid of the loop. And you do this carefully with carefully chosen rejection probabilities, and the output is still precisely uniformly distributed over G of D, which I think is pretty cool. And before I tell you the more precise results, improvements have been made recently, first by Gao and Warmold, and then Armin, Gao and Warmold, both extending the range of degrees for which this works and improving the runtime a lot. So this algorithm is really fast if your maximum degree is not too large. And if you can use this algorithm, you should. So in particular, in the regular case where all the degrees are the same, D, if D is little o root n, which means D over root n tends to 0, then you get essentially expected runtime the order of the number of edges. Dn is the number of edges, but it might be D to the 4th if D to the 4th is larger. In the non-regular case, we get order number of edges runtime, so at most some constant times the number of edges, expected runtime if the maximum degree to the 4th is growing slower than the sum of the degrees or the number of edges. And you can't describe a graph in less than order of m runtime, I think, unless you're doing something pre-arranged and clever. So this is sort of as fast as you would expect. And Gao and Warmold also had an algorithm for power law degree distributions, one of these heavy-tailed distributions, which Armin, Gao and Warmold improved the runtime to order of linear in the number of vertices. I don't want to define power law degrees, but there's an exponent, gamma, which is typically taken to be between 2 and 3 for real-world networks. And their algorithm can handle exponents which are close to 3. I think it's about 2.87 and above, but still it's very fast. And the first two have asterisks next to them because those two have C code available for download from Nick's website. So if you ever did want to generate graphs with given degrees, I would recommend this code because it's the best that we have. Okay. But it still has upper bounds on the degrees. So what do you do if you have a situation you don't think fits into one of these, or if Nick's code is too slow, I should say, Nick, Jane, and Andre's code? Well, what's left is you can try a Markov chain. There is one other approach based on sequential importance sampling, but it doesn't beat this algorithm. And Markov chains is the approach that I've worked on the most as well. So I'm going to give you a quick tutorial about what you need to know about discrete time Markov chains. So here's a little Markov chain running on a cube. The current state is a vertex of the cube. And at each time step, it just decides which edge to walk along randomly from the 3 edges it has. So a Markov chain is some random process that takes discrete time steps and decides what to do next based only on where it is right now and not on how it got there. Okay, so it's walking and it might go back. Anyway, it walks around. It's walking on a set omega, which is called the state space. And a nice Markov chain, an ergodic one, which I will tell you a bit more about what ergodic means soon. If it's ergodic, then it has a unique stationary distribution and it converges to this stationary distribution, which means if the state is distributed according to pi, then it stays distributed according to pi forevermore. And if it converges quickly enough, then you can use this Markov chain for sampling. So you just run it from some initial state for capital T steps. And if you know that after capital T steps, you're sufficiently close to uniform or sufficiently close to stationary, then you can spit out the Tth state as your output and start again. You need some bound in advance on the number of steps required for this though. So this would be easy if the state space was small, but the state space is typically exponentially large as the function of some parameter n. And so we're going to say the chain is rapidly mixing. If it gets sufficiently close, which I don't want to tell you how we quantify, but we can, in time bounded above by some polynomial in the logarithm of the size of the state space. So this is theoretical computer science point of view. Any polynomial is a good polynomial. Thank goodness, because some of the polynomials we get are pretty bad. I'll say something about that shortly. Now, if we knew the transition matrix, in particular the eigenvalues of the transition matrix, we would know exactly how fast this chain converges to stationary. So the transition matrix is a a big matrix with rows and columns indexed by the states, and pxy is the probability that my next step takes me to y, conditioned on being at x right now. Notice that I'm assuming this is independent of time. So I'm actually restricting myself to time homogeneous chains, because I make the Markov chain as nice as it can be before I even look at it, basically. The problem with this, of course, is that the state space is exponentially large, so we cannot calculate those eigenvalues in polynomial time. You have to kind of sneak up on them and get some bound on them somehow. Okay, so we're really, unless you do a probabilistic argument, you're trying to get a handle on the eigenvalues. And how we try to do this for the Markov chains on graphs is looking at the geometry of the state space. If you're walking around on the state space on the right, you can see there's a bottleneck of some kind. It's difficult for the chain to get from the left side to the right side. And if the stationary distribution gives at least some constant fraction of the weight to both sides, then you can see it's going to take a long time for the chain to converge because it has to escape through this narrow bottleneck. And it leads to exponential time to convergence. And on the other hand, if you don't have any constrictions, like the picture on the left, then you get polynomial time convergence. And there are results by Jerome and Sinclair that allow you to quantify this using something they called conductance. So that's nice. That's what we want to do. There's a relationship between this conductance and the eigenvalues. But how do you try to get a handle on whether your state space has any constrictions? So the method that we tend to use is called the canonical path method. For any two pairs of states, you have to define a path, one particular canonical path between them, and each step in this path is a transition the Markov chain might take, okay? And once you've defined a path between each pair, you look at the set of all paths, and there's a parameter called the congestion, which it doesn't hurt too much to think about it as the number of paths that use a particular transition, and you take the maximum over all transitions, except that there might be some weighting to do with the length of the path and also the probabilities of the endpoints if it's not uniform. But essentially, you're counting paths. If there's no transition that's heavily loaded, you can't have a bottleneck, because if you had a bottleneck, you can imagine those transitions are getting pretty hot, all the paths are going through them. Then results of Alistair-Sinclair allow you to go straight from the congestion parameter, which I'm not defining formally for you, to the mixing time of the chain, okay? So that's the game we would like to play. How do we do this for sampling graphs with given degrees? Well, you often want to look at nice local changes. They're easy to analyze. So the smallest change you can make to a graph without messing up the degree sequence is to remove two edges and put them back in one of two possible other ways, right? We call this a switch. And a switch chain is just a Markov chain that performs a random switch at each step. I'll show you the pseudocode that I tend to use on the next slide. But hopefully you can see that if you perform this many times all around the graph, you're going to randomize your graph and forget about your starting point and hopefully reach a uniform, converge towards a uniform stationary distribution. And you can also use this sort of thing in something like a communication network, a peer-to-peer network, to sort of heal after failures or whatever. But here's the pseudocode for the switch chain. So you're at some current graph with the given degree sequence. You grab two non-adjacent edges uniformly at random, non-adjacent, so you have 4 distinct vertices. Choose a perfect matching of those 4 vertices uniformly at random. Well, there's just 3 ways, including the 2 edges you just selected. Then you think, if I remove my 2 selected edges and put the perfect matching edges in, am I creating any multiple edges? Because we don't want that. If you're not creating any multiple edges, you go ahead and make that change. You rip out the 2 initial edges and you put in the edges of M. And otherwise you just stay put and it still counts as a transition of the chain. Okay, and uniformly at random is UAR. So that's how we do our switches. First thing we observe is switches connect the state space. You can get from any graph with a given degree sequence to any other using a sequence of switches. Now, last time I talked about this, I said this was due to Taylor, and then one of the people, actually Brendan, sent me an email saying, I don't think so. Taylor was an Australian mathematician, and he may have been the first to write down the proof for simple graphs. Brendan said Reiser had also used switches. I think that was for multigraphs though when we looked into it. And then I remembered a co-author of mine, Peter Erdős, no relation to Paul Erdős, told me that Peterson used switches in a paper of his in 1891. And the first time I looked into this, I couldn't find it, and I didn't believe what Peter Erdish had told me. But for this talk, I looked into it harder, and it's true. So that's luckily I did German in high school, so I could sort of fight my way through this. But we are replacing edges A, B, C, D with edges AC, BD or edges AC, BD. And Peterson stuck to regular graphs with even degree because he was actually using Euler tours to help him in his proof, although he didn't call them Euler tours, and it's not clear whether he was aware of the Euler tour result. But anyway, he did prove this result, at least for regular graphs of even degree. Anyway, so it's well known this is true, but it's harder to figure out who we should be attributing it to. Secondly, because you might choose exactly the same two edges to put back in that you took out with probability a third each time, you stay where you are with probability at least a third at each step, which might sound dumb, but it actually helps prove that the chain is something called aperiodic, which I'm not defining for you, but connecting the state space plus aperiodic is ergodic, which is exactly what we want to get the guaranteed unique stationary distribution, which is a limiting distribution. So that's good. Our chain is nice enough to look at. And we can also see the stationary distribution is uniform. This sort of makes sense when you think of the transitions because we weren't really putting any bias one way or the other, but we check it using something called detailed balance equations. So if pi is any distribution and it satisfies these equations, then it must be the stationary distribution of the chain, assuming the chain is ergodic. So this is a good design tool for making sure your Markov chain has the correct stationary distribution. In particular, if P is symmetric, then your stationary distribution is uniform. Okay, good. So we're all right. Our switch chain is nice. We want to analyze it. People have analyzed this, and it's known to be rapidly mixing in a wide range of degree sequences. I'll just mention a couple of the relatively recent results that pull a lot of things together. So there's a thing called a p-stable family of degree sequences, which arose from early work of Jerram and Sinclair from 1990. With Peter Erdish and his team, we were able to prove that the switch chain is rapidly mixing whenever the degree sequence is p-stable, whatever that means. And then with Jane Gow, we were able to prove for the first time that heavy-tailed distributions, the switch chain converges rapidly. And rapidly means polynomial time. Now, pretty much all of the proofs we know, either they use a multi-commodity flow argument or they rely on results that had been proved using a multi-commodity flow argument. And a multi-commodity flow argument is just a generalization of a canonical path argument. So instead of just one path between two states, you might take a finite set of paths and sort of average your flow over all of these paths, and it helps you smooth out the flow even more to try to avoid congestion. The downside of this is you get high degree polynomials. This method does not tend to give you nice bounds. And they're believed to be very far from tight. So we go yay from a theoretical computer science point of view, but not yay if you really actually want to run this on a computer, because, I don't know, n to the 9th, d to the 23rd is not very appealing. Something like that. And a recent exception is very impressive and difficult work of Tikhomarov and Youssef, who looked at deregular bipartite graphs, where the vertices are in one side or the other and edges only go from one side to the other. And they got n log n mixing time with a constant out the front. And this is optimal up to the value of the constant out the front. So you really can't do much better than this. It's a huge improvement on any other bound that we knew before, except their own previous work, which was also very good. They use something called a modified log Sobolev inequality, which is a much more direct way to bound the eigenvalues. So that's why they were able to get a much better result, but it's extremely technical and impressive work. Okay, so that's what I want to say about the switch chain. And in my remaining time, I want to talk to you about more recent work with Colin Cooper and Martin Dyer, where we asked ourselves, what if you don't just care about the degree sequence, but you also care about some other features? And one motivation possibly for asking this question is looking at social networks. So in a social network, you tend to see a lot of triangles. And this has been observed since at least 1908 by sociologists, the friend of your friend is likely to be your friend, right? If you have those two edges, you're likely to see the third edge. So how good is G of D, the graphs with given degrees, at producing triangles, we can ask? Well, the expected number of triangles in a uniformly random graph with degree sequence D is given by this expression here, mu. The definition doesn't matter too much, but since this M2 is bounded above by at most D max times M, the sum of the degrees, mu is bounded above by D max cubed over 6. And if it's regular, it's equal to that. In particular, if D max is constant or not very big, then the number of triangles is also going to be constant or at most not very big cubed, right? And you get a asymptotically Poisson distribution of the triangles in that case, even for slowly growing degrees, because the sum of rare events, the number of rare events is asymptotically Poisson. And this is not the sort of number of triangles we want to see. This is too small. So if you're interested in a social network, then a random graph from G of D might not be a good model, even if the degree sequence is correct. What can we do? So what we decided to do was just adapt the switch chain so that it allowed us to play with triangles a bit. And what we decided to work with was a subset of the switches, so a restricted set of switches, which are called triangle switches. And a switch is a triangle switch if it changes the set of triangles. So from left to right, we create a triangle, and from right to left, we destroy at least one triangle. Okay. The first question you might ask is whether triangle switches, which I'm writing with this little triangle switches, whether they still connect the state space. And someone remarked to me after a talk that you could think of this as a sparsification of sort of graph and whether it's still connected, the graph underlying the Markov chain. Okay. Complicating matters, as you might have already thought to yourself, is that one triangle switch can affect a lot of triangles. You might be designing this to insert a particular triangle, but you could also be creating or destroying a whole bunch of triangles. So this can make life a little bit difficult, and it's something to keep in mind. Okay, so our first sort of foray into this was some work on the regular case when the degrees were at least 3. And we used a combinatorial argument, which looked like this. Take a D-regular graph on n vertices. We showed that we could perform a sequence of triangle switches to turn that graph into one with this very rigid structure. It's a union of cliques, so complete graphs on D+1 vertices. Those are D-regular. If D is 3, they look like this, okay? And at most one little fragment, which is too big to be a clique on D+1 vertices, but too small to break up into 2 cliques. So we showed we could transform any graph in G and D into one of these, and then we showed that we could use a sequence of triangle switches to map any one of those into another. So putting that all together, you can get from any graph to any other graph in G and D using a sequence of triangle switches, right? So problem is it didn't extend very well to irregular, but a more serious problem, I think, is these are terrible, terrible, terrible paths if you want to think about rapid mixing. Why are they so terrible? Because you've got this massive state space, and the subset, which has this very sort of rigid structure, is a tiny, tiny fraction, much smaller than this. This is not to scale. And you're sending every path through this tiny little region. So you're artificially creating a bottleneck. So this is almost optimally bad choice of paths. We weren't thinking about mixing at the time when we did this first one, right? So we have to do something different if we want to do a mixing proof using canonical paths. And so that meant we got to do another paper on this stuff, and we've restricted ourselves to degree sequences with the minimum degree, every degree being at least 3. And we proved that you can simulate every switch using a short sequence of triangle switches, at most 5 triangle switches. The proof involved a combinatorial argument. I'm going to show you how one of the cases works in a second. There were several cases, but the point is we know that switches connect the set G of D. So between any 2 graphs with a given degree sequence, we have a sequence of switches between them. It might be a lot longer than this. And now we can replace each switch by a short sequence of triangle switches, and you have a path involving triangle switches that get you from X to Y, and you're done, right? Okay, so how do we do this? Well, if your switch is already a triangle switch, it changes the set of triangles, there's nothing to do. Otherwise, well, let's label the vertices A1, A2, A3, A4. The original edges are 1, 2, 3, 4. The edges we want, put the odds together and the evens together, and none of them are in a triangle or would create a triangle if you inserted them. So what you look at are the remaining two edges, A1, A4, A2, A3. We're going to call them the diagonals, and their indices add up to 5. That's how you're going to recognize them on the next slide, okay? So we looked at whether the diagonals were present or absent, how many common neighbors they had, blah, blah, blah. And one of the cases we had to look at is the one I'll show you on the next slide. Let's not read this description, let's just look at the picture. So the setup is like this. Now I've drawn the edges we want to get rid of are vertical. The edges we want to insert now look like they're the diagonal ones, but the edges I was calling the diagonal, I've just redrawn them so they're horizontal to make the picture look better. These are the diagonals A1, A4, and A2, A3. We can't just do this switch because it's not a triangle switch, but we can do this switch, which takes out a diagonal, takes out this edge UV that in this case we know is present and blah, blah, you get to this situation. Now both your diagonals are absent. So we can remove the edges we want to remove, A1, A2, and A3, A4, and we can insert the diagonals, and I should be getting you to check each time, are we creating or destroying at least one triangle? So in the first step, we created a triangle on A2, A3U, for example, and we destroyed some other triangles. So at each step, we need to check, are we creating or destroying a triangle? And you can see that we are here. Now our diagonals are in, the edges we wanted to remove are out. We can insert the edges we need to insert. And by doing that, take the diagonals out again. So we make that switch. It's also destroying and creating some triangles. And this is more or less what we want. We've achieved what we want on the switch edges, but we've messed up 4 other edges. So the last step is just to put the 4 other edges back. Okay, and that's also a triangle switch. It changes the set of triangles. So you just have to find a way, an argument like this in all of the cases that arise. We have simulated this switch using a sequence of 4 triangle switches. Okay, make sense? So that's connectivity. What about mixing? And how can we define the transition probabilities to encourage triangles? We know that the uniform distribution doesn't do it, so we want a different stationary distribution. And we're going to use some ideas from statistical physics, statistical mechanics. We're going to use a Gibbs distribution. So we take a parameter lambda, at least 1, and T of G will be the number of triangles in the graph G. We want our stationary probability pi of G to be proportional to lambda to the number of triangles. This is like the energy of the graph in this system. Actually, I forget whether lambda to the T or T is the energy, but anyway, it's something to do with energy. And the normalizing factor Z lambda is the partition function of this system. So this is our target probability distribution, because if lambda is strictly bigger than 1, then triangles are encouraged. And if lambda is really big, then triangles are encouraged a lot. You get a factor of lambda, more probability for each triangle that you have. Okay, so here's the pseudocode that we used. It looks a lot like the switch chain. You, from your current state, grab 2 non-adjacent edges randomly, choose a perfect matching of those 4 end vertices randomly, create the graph that you would get by deleting the 2 chosen edges and inserting the edges of the perfect matching. And then you check, firstly, is it a valid switch? It doesn't create any multiple edges. And secondly, does it change the set of triangles? So is it a valid triangle switch? If it is, we're going to move to H, not necessarily with probability 1 like we did before, but with probability 1, the minimum of 1, and this lambda to the number of triangles in H minus the number of triangles in G. It's actually pi of H divided by pi of G. Okay. If H has at least as many triangles as G, you move with probability 1. But if you're going to reduce the number of triangles, then you're a bit more hesitant. You're not as likely to move to H. And that gives you a bias towards the graphs with triangles. Now, this is the metropolis setup, and it always gives you the stationary distribution pi that you want. So if it would obey my request, The point is P of GH before was symmetric. Now it's proportional to this minimum of 1 or the pi of H divided by pi of G. And you can check for yourself. I'm not really going to give you enough time to read this, but the detailed balance equations hold with this transition probabilities. And that means that pi is the stationary distribution, as we saw before. Okay, is there something else? Yeah, we know that pi is what is the distribution we're going to get in stationarity. And now the question is, how long will it take to get there? Okay. So the first thing we had to do was look at the number of triangles, the distribution of the number of triangles under the new probability distribution pi. So we proved that if this condition holds, D max log lambda is the low log n. When you take a random graph using the distribution pi, the number of triangles is asymptotically Poisson more or less, and the mean has changed from mu, which it was before, to lambda times mu. So the expected number of triangles has gone up by a factor of lambda. I say roughly because it kind of breaks down in the upper tail. So it looks asymptotically Poisson and then things get weird at the end. And mu is the expected number of triangles we had before in the uniform distribution. Okay, here's our main convergence result. We have a family of graphical sequences. They all have degree at least 3. Lambda is greater than or equal to 1. It might depend on n. We suppose we had to take a parameter alpha between 0 and 1. And our assumption, which is way stronger than we would like, is that lambda times mu is at most log n to the alpha. So the expected number of triangles that we can hope to get is at most log n to the alpha, which is less than we were hoping, but at least we could prove something in this setup. And it's a conditional result. If the switch chain mixes rapidly for degrees in this family, then so does the modified Metropolis triangle switch chain. Modified, I'm sneaking in, I'll have to explain what that means. But basically, if the switch chain is okay, then so is the modified Metropolis triangle switch chain. Okay, so what's going on here? We reuse those simulation paths we had before. So because the switch chain, if we assume the switch chain mixes rapidly, you can get a good set of canonical paths with a low congestion for the switch chain. Replace each switch by our little short sequence of triangle switches, and now you have a set of canonical paths for the triangle switch chain, the Metropolis triangle switch chain. And we had proved a theorem in an old paper. We called it the two-stage direct canonical path construction method, which was a bad mistake because there's way too many words and no one's ever going to remember the name of this method, but it's set up to do exactly what we want here, to analyze how much the congestion can get worse by, compared to the canonical paths that you start with for the switch chain. The problem that we found when we were doing this analysis is that necessarily, when you look at lambda to the T of G, the impact of the tail of the distribution when you have a lot of triangles just overwhelms everything. It completely blows up and we can't control it and we don't get a polynomial bound. So the modification that we did was to say, in the stationary distribution, you get a factor of lambda for each triangle only up until a certain cutoff, which we called nu. And after that, the triangles just give you a factor of 1. They make no further impact, okay? And we chose nu to be log n over log n because that gave us what we wanted. So we've adjusted the stationary distribution, but you put it through the Metropolis scheme in exactly the same way. And the result was, if our condition holds, then ever seeing more than nu triangles has a smaller probability than any polynomial, which means if you run the 2 Markov chains for a polynomial number of steps, you're very unlikely to see any difference in their behavior. So we think it's okay, this modification. That's our first point. And secondly, we were able to show that the congestion goes up by at most a polynomial factor. This polynomial factor shows up in the mixing time. So this is good from the sense of it gives us polynomial mixing, bad in the sense that that is a much more restricted condition than what we were hoping for. So that's our recent work. Couple of final questions. Did we make the right choice with the Metropolis chain to begin with? If you're looking at trying to encourage triangles, like there's lots of other choices we could have made, or a better analysis method. We compared the weight lambda all the way back to the weight 1 case. Was there something we could have done? I wonder if we take sort of stage posts in between, whether we get some better result, or I don't know. And secondly, a more high level question, is there any algorithm out there that will do efficient, uniform or almost uniform sampling for any degree sequence? We don't know of any. We don't know of any degree for which the switch chain doesn't mix rapidly. So we know that this p-stable class, although big, is not the true boundary. We do know some degree sequences for which the switch chain mixes rapidly, even though it's not p-stable. So maybe the switch chain always works. We just don't know. Works in the theoretical computer science sense. And that's it. Thank you.
Thank you, Catherine. Do we have any questions for Catherine? I had a quick question for you.
Okay.
Do you remember the bottleneck picture that you showed?
Yep.
And you mentioned that was exponential time.
Yes.
Is that a function of how narrow that little bottleneck is?
Well, I guess the bottleneck is kind of a cartoon. So it's not just the state, it's also about the transitions of the Markov chain. So what it's meant to indicate is that there's a very small way of getting across the bottleneck. So in one example that's well known is if you picture a bipartite graph with the vertices in two sides and all the edges go from one to the other, and you're looking for independent sets in this bipartite graph, and that's a set of vertices which don't contain any edges. You could take a big independent set on one side or a big independent set on the other, and there's lots of those, but it's very difficult to move from an independent set, which is mostly on the left, to an independent set mostly on the right, just by removing and inserting vertices. So in the state space, there's a very small area, which is a sort of mixed independent set, and it's just exponentially small relative to the rest. And all of the canonical paths have to go through this tiny area. So I guess that one, it is about the state space, but sometimes it's about the transitions that the Markov chain takes as well.
Okay.
I don't know if that answers your question.
I mean, but if I start shrinking that little gap as small as I can, like smaller,
Right.
Is there some kind of...
Well, eventually you'll disconnect the whole.
Right. So, I mean, is there some kind of relationship with the time and the size of the gap, or?
Yeah. So the Jerram-Sinclair result works on something they call conductance, which is like a kind of surface area to volume ratio. And so I guess, yeah, I've just lost the thought I was having. If there's very small ways of getting out of a set compared to the size of the set, which would be the case if you had this really tiny bottleneck, there's a quantifiable relationship. And I think it's proportional to, like, you get lower and upper bounds proportional to either the conductance or the conductance squared. So it controls both sides.
Okay.
Yeah.
And is it a function of the dimensionality? Sorry, I'm asking too many questions.
So I think, from memory, the conductance is the probability that you go from S to S complement divided by the stationary distribution of S, and you take the worst case over all subsets S that have pi of S at most a half, something like that. And so it involves the stationary distribution, the transition probabilities, and the sets in the chain. Yeah.
Okay, thanks. Big flash. Oh, sorry. Sorry.
So thank you very much. I actually have two questions, and I'm a physicist, so
okay,
they might
great.
be ridiculous. So the first one is, so you've mentioned, I mean, there's a lot of I think connections from what you were saying to showing to classical physics, but I was thinking that if one wanted to apply that to quantum physics, one of the first things we do is we drop the assumption about distinguishability of the vertices. Is there a version of that theory that?
So usually it's much easier to work with labeled graphs. Yeah, I don't know of much work on unlabeled graphs, but when you take a random graph from a big family, as I said at the start, I mean, for regular graphs, for example, the probability that you have an automorphism tends to 0. So in that sense, they're the same. So it might be possible to pull results over just by saying most of our graphs don't have any automorphisms anyway. Yeah. Okay,
and the second question is, so the case of, say, triangular connections within a graph, that's a very specific case, right?
Yes.
Are there any other very characteristic features in other graphs that you study?
This was the only one that we've looked at. So I think people do look at other motifs, and there's this exponential random graph model where you can put weights in front of counts of various different motifs and sort of adjust your weights to try to produce a graph with the desired properties, maybe lots of this and very few of this or whatever. We just started with triangles because we could justify it by saying social networks, don't ask me any questions. And also, it is something that people look at. But if you're prepared to work at it, you could probably generalize it. Yeah.
Thank you very much.
You're welcome.
I was thinking similar things to Nikolai. I'm also from physics. I was also thinking you're defining an edge to be an edge or not an edge. What if it's an entangled edge? What if it's got a probability of being an edge? Can you create the space of graphs by putting probabilities of edges on on your nodes?
I mean, yeah, I guess you could always throw edge weights that might represent probabilities.
And that would then create the space of possible graphs.
Yes. So one issue the way I work is with finite sets. So I might want to discretize that probability so that I don't suddenly have an infinite, continuous, scares me. But you could probably I guess you'd have to decide for, figure out what transitions are sensible, and then you could probably do the same thing.
Because you're using a lot of terms that are familiar to me from a completely different perspective.
Yes, there's a big connection with statistical physics, and we often have workshops where you have theoretical computer science people doing this stuff, statistical physics. A lot of problems, actually, the Markov chain approach had been put aside because there are these correlation decay algorithms that come from statistical physics, which were performing as well or better, not using any randomness. And then from there, we had methods that involved proving that certain polynomials have no complex roots within a certain region and doing some polynomial interpolation. These three approaches seem completely different. And now people have found connections between these three approaches that have allowed them to go back to Markov chains and use a method called path coupling, which is different to this, but it's the first method that I used when I was working with Markov chains, and get new path coupling proofs to work using ideas that have gone all the way through this thing, which I find fascinating, and I wish I knew more about.
It's nice to see the links. Actually.
Yeah, absolutely.
Yeah.
So you started by talking about these binomial random graphs.
Yep.
So in that case, if you increase your number of vertices so that it becomes infinite, then as I understand it, you, with probability 1, get a particular graph.
Yes, you've got this universal random graph then, and any graph you can think of is a subset of that graph somewhere, I guess an induced subgraph or something with probability 1. So
So
weird.
do you know anything about what happens with these other kind of selection algorithms if you let your number of vertices go to infinity?
I guess if you let the number of vertices go to infinity, but you keep the degrees, I mean, it wouldn't make much sense for a 3 regular graph, I suppose, because there's so few. I don't know. I haven't actually thought about this. Maybe some people do, but I've always thought it made a bit more sense in the binomial random graph model. What people actually do is think of the adjacency matrix of your graph, draw it in a square, and put black dots if the edge is present and white dots if it isn't. And then you let n tend to infinity. And now you've just got a map within a square. So you sort of scale everything back down, some bits are black and some bits are whites, and that's a graph limit. That's a bad explanation of a graph limit, but people study graph limits and then infer results about really big graphs. And so graph limits are all very continuous. I've never worked in graph limits, but LOAS, for example, people who work in random graphs have also looked at graph limits.
Thanks.
Can you say a bit more about connectedness in a graph? Like, what do you do with a graph is disconnected to start with? Do you throw it away like the generation of graph, or do you actually, can it work actually on disconnected component and you just then change?
You mean so you're talking about the graph itself is disconnected, not all the state space is disconnected.
The graph with all level from 1 to n is the one you get given is actually disconnected.
Right.
And you don't know in how many components.
Okay.
It's giant.
So the idea of analyzing the switch chain came up because someone handed me a paper about a peer-to-peer network protocol that they'd worked on. And it was just switches. It was beautiful working on regular graphs. But eventually one of the things we said to him was, this could disconnect your space. If you've got a communications network and you do if you've got 2 edges going from one side to the other and you switch them away, boom, these guys can't talk to these guys. they said, oh, we just don't think that happens very often. And it's true, it wouldn't happen very often. But you can look at another restriction, which is where you only do the switch if there's a path between the two edges. And the strictest version of that is edge, 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 right? And you just swap like this, and that's called a flip. So we also analyzed that for connected graphs and showed that it was, I can't remember. I think we only looked at regular and showed that it's always connected, and you can do nice analysis.
It seems in your algorithm that if it's connected a distance to, it stay connected. Maybe not a distance to, maybe larger distance, but stay connected.
Yeah. So the only thing you have to worry about is if you have a double, I don't know what you would call it, an edge separating set of two edges, and you take it out, and yeah. So it's rare that you would see that, I guess, but it could happen. And if you don't want it to happen, you shouldn't use switches. You should use what we call flips. Yeah.
I just want to echo the point that Judith made about, there are so many concepts that are present in other studies. And at some point I saw that, you use the word ergodic.
Yep.
You use the word transition matrix.
Mm-hmm.
You use the word eigenvalues.
Mm.
That is actually very close to some of the investigations I've been doing recently about the distribution of geodesics. Okay. On surface, flat surfaces, and there, you start with a short section of a geodesic, mm-hmm. and then you can gather some information about a longer section of a geodesic, and that's where the Markov chain comes in. Right, yeah. Right? And the next you end up with a big transition matrix, and there you have to find the two largest eigenvalues. Ah, yes. If you can find the two largest eigenvalues, it tells you the quality of the uniform distribution. Right. So, of course, the hard bit is that a lot of the time, the transition matrices are huge. Yes, yes, right? Exactly. And then you have to look at some other means to actually, because there's a lot of redundant information. Yeah. Two eigenvalues, the two largest ones, you don't need the rest. Right. So you need to find some way to find these eigenvalues. I mean, that's a different question. Yeah. But the original approach to actually look at the problem is just the Markov process. Yeah. Transition matrix, eigenvalue. Yeah, a lot of people work with Markov chains, and some of them have continuous space, continuous time, and the questions are different, but some similar ideas coming up. And the word ergodic is interesting because when you study dynamic systems, using ergodic theory, you can only get time qualitative results. I see. Because, the ergodic theorems that you use don't have error terms. So you can't say anything about the quality of the distribution. You only know that it's uniform. Right. And this approach using the Markov process actually gives rise to good statements about the quality of the distribution. Yeah. Mm-hmm. One more question.
Yeah. Yes. Thank you so much for the wonderful talk. And regarding the second final questions, so basically, one question is, can we perform efficient uniform generation for any degree circus D? But also, perhaps we can think D itself is actually random. So basically, D is in a place. So then, can we generate? Can we have efficient uniform generation for some kind of like randomly distributed D, which actually has a large probability on those good Ds and have some small probability on those kind of really weird D. So can we do that?
Yeah, so I guess the only way I would have worked with it does that would be you just choose your random degree first and then go ahead and sample from my set of just that degree. Right. But as I mentioned, there is a Chung-Lu algorithm that gives expected degree sequence. Right. I forget how that works now, actually, but there could be other work in that area, in that direction that I'm not aware of. So I do look at something quite specific, I suppose. Yeah.
Thank you.
You're welcome.
Okay, I think people are hungry, so let's thank Catherine again. Thanks, Catherine, for a great talk.
Thank you. Thanks for inviting me.